Hey everybody. In this video, I'm going to be talking about a couple of things relating to drones. I have two DJI drones, the Inspire 1 Pro with the X5 camera drone. It's about a year old, and just recently, a couple months ago, I picked up the DJI Phantom 4 Pro drone. And, flying in the wintertime, as it's pretty cold in Utah in the wintertime, you have a problem because both drones operate from batteries, LiPo batteries, and LiPo batteries and cold weather are not a good combination. So what I did was I repurposed a cooler as a heating unit. So I put 5 or 6 batteries in here, and I can use either the Inspire or the Phantom batteries. I built a temperature controller for it that I can power from a repurposed laptop power supply that delivers 19 volts. Or I can use a car adapter that operates from 12 volts. So I have a buck converter in here that takes the voltage from either the laptop power supply at 19 volts or the car at 12 volts, and it outputs to the controller about 11 volts. And depending on the temperature outside, I would generally run the heating unit here at pretty much a minimum of 25 degrees C when it's not that cold out, say in the 40 degrees, 5 Celsius range. But when you get colder than that, around about freezing point, 0 Celsius, 32 Fahrenheit, you probably want to go up to about 30 degrees in the controller. And of course, the controller is in Celsius. And if you get colder than that, then you can up the temperature to, I wouldn't go above 40 degrees C. But if you get down to like 0 Fahrenheit, and that's around about, minus 20, close to minus 20 Celsius, then you probably want to be up around 35 degrees as your battery set temperature. And the reason for that is, you're running it in the cooler. You have that in your car, for example. So your battery's at, let's say, 35 degrees, and it's minus 20 Celsius outside. By the time you get the battery out of the heater, put into the drone, and get the drone into the air, it's going to take you maybe a couple of minutes, maybe 3 or 4, maybe 5 minutes. So in that time, the temperature of the battery is going to go down, and you don't want it to go down much below about, I would say, 30 degrees C when it's that cold. I did a flight a couple of weeks ago when I first tested it. It was 28 Fahrenheit, so a little bit more than minus 2 Celsius. And I had the heater set to 30 degrees Fahrenheit, 30 degrees Celsius. And I found that that worked out pretty well for that flight temperature. The data on the battery during the flight showed that it increased a little bit in temperature from about 30 degrees where it started to about 35 degrees or less. I mean, it didn't change that much. So I think the temperature that I set for the heater at 30 degrees Fahrenheit was a pretty good match for the temperature outside. So that was the idea behind this, and I'll bring the camera here in a minute so you can get a closer look at it. So again, I have the power supply plugging into it. I have a buck converter with a little fan here to cool the buck converter. That outputs voltage to the control board. And again, I'll bring the camera in a little closer in a minute. And it's the control board then controls temperature in the heating unit. So let me bring the camera in a little closer and you can see what I'm talking about. Okay, so that's the unit, and you can see I've got a temperature control board, the power supply, main power supply for the unit. Again, buck converter here, fan, and then it outputs voltage to the controller, and it's basically on-off control. So I have the set point at 30 degrees. When it reaches 30 degrees, it shuts off, and there's a little LED right there which tells me right now the heating element is off. And when it drops below 29 or hits 29.9 degrees, then that LED comes on telling me the heating element is on. Looking inside, and let me turn another light on here to make it a little easier to see. Okay, so inside here I have 4 batteries right now, and let me take them out so you can see a little bit better. Take a couple of them out. So what I have is some aluminum plates with 2 40mm fans. This is forced convection heating. And I have some heating elements, basically power resistors, bolted to the bottom side of the aluminum plates as the heat source. That heat is then spread through the aluminum plates, and then the fans circulate the heat around. My thermistor here for temperature monitoring is right there. So that's basically the operation, and the fans are on all the time. Whether the heating element is on or not, the fans are on. So let me put these back in, and you'll see the temperature will have dropped. Obviously the thing's been open for a bit. So we're down to 28 degrees, and you can see that LED is turned back on again. This little LED right here. So we're at 28. It'll come up again pretty quickly. But the other thing I wanted to talk about here is that this little board, and let me get the original one that I had so you can see that a little bit better. So let me put that there. Turn that around. So that's the original one, and it has a relay on it. And relays are not really the ideal setup when you're switching DC current. So what I did was modified my second board by replacing the relay and using a power MOSFET, this guy right here, in place of the relay. So the rest of this video will be detailing the modification process of the temperature control board to operate from using a MOSFET. Okay? Well, hello. This is the temperature control board, and it's basically on-off control. A thermistor plugs in here, and this here is the thermistor. So that plugs in here. That basically monitors the temperature. The microcontroller over here monitors the voltage, the temperature, and depending on the set point you set for it and the hysteresis you set for it, it provides an on-off control through this relay, which provides switch closures to K0, K1, and so then you can apply power to a heating circuit or a cooling circuit, whatever you plan to use it with, and the current is controlled through this relay. Problem, of course, is that relays and DC are not a great combination. AC is preferred when you're using a relay because you have 100 to 120 times per second AC automatically shuts itself off when the voltage goes to 0. With DC, you have to open the contacts on the relay sufficiently that the arcing stops. And you're going to have arcing pretty much all the time, even at relatively low voltage and relatively low current. So this is a failure mechanism for particularly DC related circuits, but even using it in AC, if the switching frequency is high, then sooner or later the relay is going to fail mechanically. So what I'm going to do in this modification is replace the relay with a P-channel MOSFET. And the reason for the P-channel MOSFET versus the generally preferred N-channel MOSFET is that it's just an easier swap. You have basically replacement of the relay with a MOSFET and a couple of resistors to bias it and control it properly, and that's it. So it's a very simple fix and requires no downstream modification to the existing circuit. So let's start with the a sketch of the circuit of the board as it's originally shipped before modification. Voltage comes in generally about 12 volts, and you can vary that, of course, but let's say 12 volts come in. I'm calling that V in. It has a protection diode here, D2, to prevent connecting reverse, apparently a current limiting resistor of 10 ohms. And so the output of that, going from about 12 volts in, at the output of the resistor, we're at about 11 volts. And that 11 volts is then fed into IC2, which is an AMS 1117 SOT 223 voltage regulator, whose function basically is to generate 5 volts for the microcontroller. So we don't need to really talk much more about that, other than the fact that we have essentially 2 plus voltages, or 3 plus voltages. You have the plus 12 coming in, the plus 11 approximately at the output of the current limiting resistor, and then the 5 volts for the microcontroller. So we have plus 12 and plus 11. And it's actually the plus 11 that's used in the original configuration to pick the relay. Q1 is an NPN resistor, transistor. I think that's an S8050. It's a SOT 23 transistor. And the microcontroller, obviously monitoring the temperature, will either turn Q1 on or off depending on its need. So when Q1 is turned on, that pulls current through the relay coil, which turns the relay on, closing the contacts, and then allowing for voltage going through the relay contacts to the heating element. And it's the heating element that's the sort of the business end of the circuit. This is not part of this unit, but is the actual load. So in operation, if the temperature is below set point and the microcontroller turns Q1 on, then the relay is turned on, which takes the V plus or 12 volts, connect it to K1 contact, and then connects it on through K0 and on to the heating element. The other end of the heating element is tied to ground, so we get current flow and heat generated in the relay, in the heating element. As the heating element heats up the unit and then the temperature rises above set point, then Q1 turns off. The relay turns off, interrupting the current path to the heating element, so the heating element turns off as well. So that's the configuration that's the configuration as it comes from the factory. What I'm going to be doing, however, is modifying that to replace the relay with this MOSFET, P-channel MOSFET transistor. And it's an IRF 4905, and it's appropriately spec'd for this application. It has a fairly low, for P-channel in particular, fairly low RDS on of 20 milliohms. So with my expectation of drawing 1.5 to a maximum of 2 amps through the heating element, you know, I'm looking at power dissipation across the transistor less than 100 milliwatts and probably closer to 60 or less milliwatts. So no heatsink is required for this because the power loading, the power dissipation across it is very low. So let's just kind of go through the operation of this again. And I've eliminated most of the other circuits because this is really only the relevant change that we need to talk about. So the microcontroller sees the temperature go below set point, turns Q1 on. That pulls the gate down below the VIN by probably more than 10 volts. Should be around about 11 plus volts, which will fully turn the transistor on. So it'll take VIN, which is the full 12 volts, and switch it in through the heating element. So I'll get power to the heating element, heating up the unit. As the temperature rises above the set point, the microcontroller turns Q1 off, which pulls and then the pull-up resistor here pulls the gate up to VN, which shuts the transistor off, removing power to the heating element, and it allows that, it just cycles on and off as needed. So it's a pretty simple modification. Basically, all I have to do is, and let me remove the terminals here, wires here. I just wired it up, do a little quick looking at it. So basically all I have to do is remove this relay to pull off the, use a solder sucker to pull off the solder and then remove the relay. And I'm basically going to replace the relay with the IRF 4905 MOSFET and a couple of resistors. Pretty simple fix. All right, let's see if we can pull off this relay. So I'll arm the solder sucker. I don't think I'm going to need the solder here. Let me clean the tip. And let's see how well we do this. All right, so I'm speeding this up here. It's a little time consuming. I'm trying to remove the relay. I had a bit of a hassle trying to do that, and part of it was the board's a little wobbly and hard to hold on to. I got a clamp there that I'm using to kind of hold it in place, but definitely would have been nice to have one of those Panavice things. Definitely need to put that on my to-do list. So I futzed with this for a bit, trying to get the relay out. For a time there, I thought perhaps the relay might have been epoxied or bonded, glued or to the circuit board, but it was just the pins was hard to get out, and for whatever reason, I wasn't all that successful in pulling off the solder with the solder sucker. I did eventually get it out. But it was a bit of a pain in the rear end. Yep, definitely need to get myself a Panavice. So eventually the screwdriver lifted up the pins sufficiently to for me to finally get it off. The one pin I struggled with, and I wound up cutting the pin off of the relay and then pulling the pin out later. I should have left the pin in there and used a soldering iron to help pull the pin out, but I eventually did get it. All right, that's just about it. Pulling the last pin out, and I think that's just about got it. So now we got the relay out, and the next step is inserting the MOSFET. So let's start this here. So I've got the two resistors tied at one end. All right, so getting ready to put this transistor in. Futzed around with my flux dispenser for a bit. The needle kind of pulled out. But anyway, got that straightened out. Getting the two resistors set up to go into the board. So one end of the 22 k ohm resistor has to be connected to the V in, the plus voltage, and that's also going to be connected to the source of the MOSFET. The 220 ohm resistor is going to go to the gate of the transistor. And then the midpoint between those two is connected to basically the collector of the NPN transistor that drives it. And then finally the drain is connected to the board, and that ultimately goes to the K0 contact on the terminal board for connection to the external heating element. So once again, I've sped this up, a little time consuming doing this. And once again, having that pan of ice would be nice. The sort of this solder station here with the micro clips on it, alligator clips, it's pretty crappy if you ask me. A little too small, a little too light, and the magnifier, which you would think would be handy, just kind of gets in the way a lot of times. I wind up using a head-mounted magnifier for my own eyes, and so that the magnifier on top of the helping hands is not terribly useful. So no heat exchanger or heatsink required for the transistor. I just basically needed to solder one of the pins, and that's the drain pin, to fix it down. I may put some epoxy on it to further lock down the transistor, but it should be okay the way it is. So that's that. Just need to bend these pins and connect them up. So getting close to the end here, and just got a couple more connections to make. So I need to connect the 220 ohm resistor to the gate and make the final connection to the source, V in to the source. So let me go ahead and okay, that's done, that terminal. Now, let me bend this over. Now, probably easier to work on it like this. Trim this just a bit. See if I can put just a tiny bit of flux on that. Yes, got it. All right. So I should have this guy done here in a second. Clean the tip of the iron again. All right. So that should be it. We're good. Good, good. I'll clean this up, but I want to test this out first. So I need to hook this up and see what we get. Okay, so we're all set up to test this out. I've got the board connected to my power source, a Rigel power supply. And I've got a dummy load for my heating element, in this case a 10 ohm resistor. It's actually going to draw more watts than this resistor is designed to run, but I'm not going to run it for very long. So bottom line is I'll be able to test out the operation. So let me go ahead and turn the unit on. And let me set the set point below the turn on point. You can see the LED just went off. All right, so we're at 20.5 as the set point. Temperature is reading 22, so the unit is off. And if I look at my terminal board here, this is the ground terminal coming in, and I'm showing 0 volts. This is the plus voltage coming in, and I'm showing 12 volts. So that's the terminals for bringing power in. The next one is let me see, K1. And I'm showing 12 volts on that. So I'm basically jumping 12 volts from here to here, and that's going to the source of the transistor, the MOSFET. The next terminal over is the drain side of the MOSFET, and I'm showing 0 volts because the transistor is off. So K1 is connected to the source. K1 is connected to source, and K0, this last terminal, is connected to the load from drain to the heating element, and that's simulated here. So that's connected there, and then the other end of the heating element's tied to the ground input. So that's my circuit, and currently I'm showing the set point is low so that it's the heating element is turned off. I'm showing my power supply is delivering 12 volts at 23 milliamps and just over a quarter watt. So if I measure the voltages again, that's 0 on the ground, as you would expect, 12 on the plus voltage input, 12 on the source side of the transistor, and 0 on the drain side of the transistor. So the transistor is off, not applying any power. So let me change the set point. We'll go up to 24, whatever, when that LED turns on. There we are. So now it's on, and I'm showing 12 volts, 1.18 amps, and 14 watts. So definitely more than this is designed to take, but we won't be on for very long. Measuring the voltages, I get 0 on the ground, 12 on the input, 12 on the source, and 12, or actually 11.87 versus 11.895. Let me shut that off. So I'm really only dropping 25 millivolts across the transistor, and it's not even going to get warm. So I don't need any heat sink on that. It's fine the way it is. Now this resistor is going to be really hot because it's only a 5-watt resistor. Or is it a 10-watt? Let's see if I can confirm that. Where? Use devices. I can't remember if it's a 5-watt or a 10-watt. I think it's 10-watt. In any case, I'm not going to run this for very long. It was running at probably about 14 watts. So even if it was a 10-watt resistor, I was running it higher than it was spec for. But, you know, didn't let it run for very long. So the board works. It works just as you would expect. So time to install it. Man, that sucker is hot. All right, speeding this up again. Basically disconnecting this from the power supply for the test setup. And I'm going to be mounting that to my battery heater box, which is basically a repurposed cooler. And there it is. That was with the original configuration. I have two of these little boards. The original one that's mounted on there has the relay on it. And with the relay, just in order to reduce the amount of the frequency of it switching on and off, I set the hysteresis to 0.5 degrees. But with the MOSFET, I don't have to worry about the switching frequency, so I've set the hysteresis with the MOSFET down to 0.1. So remove the old board, installing the new board with the MOSFET on it. Inside the little black box, just below it, you can see the holes for the 40 millimeter fan, but there's also a small buck converter inside there so that I can power this unit from a repurposed laptop power supply that puts out 19 volts, or from a car power adapter, 12 volts. And the output of the buck converter is actually 11 volts. So I'm actually driving the circuit with 11 volts. So with the external power supply like the laptop feeding in 19 volts. Okay, so this is the inside of it. You can see the two 40 millimeter fans, and there's aluminum plates on top of that. The resistors that are the heating element are bolted to the bottom side of those aluminum plates. So the heat is delivered to the aluminum plates, and then the fans distribute the heat from the aluminum plates and basically force convection through the unit. Plugging it in. Now this is the external power supply of like 19 volts. I'm going to shut it off here in a second. So heating elements off, and I'm going to check to make sure that the fans are on. Fans are supposed to be on all the time, whether the heating element's on or not. And hard to see there, but yes, the fans are on. So you want the fans on all the time. And hysteresis was 0.5, turning it down to 0.1. and I check again to make sure that it's set properly. So once more back into the parameters, and it's 0.1, so it did take it. So kind of the last step here is to change the set point to 30 degrees Celsius. Had it at 30.1, and now we're at 30.0. Okay, so that's the set point. So heating elements on. I got the 4 batteries in there, starting out at 18.5 degrees, and here about 35 minutes, 40 minutes later, system's up to temperature. We're at 29.9, just below the set point. Heating element's still on, and in a second here, the heating element should turn off, and we will be at temperature. Now, of course, the batteries are still a few degrees, you know, a degree or two below the actual set point. It takes a couple hours for the batteries to actually come up to and be at set point. It takes a couple hours. All right, thanks for watching.